This is a follow-up to my presentation, nitrogen removal from natural gas, on my YouTube channel. In my previous presentation, I had discussed the use of barium ETS4 as adsorbent in a PSA scheme for nitrogen removal from natural gas streams in remote locations in order to meet the pipeline specifications. Here, I discuss an alternative scheme for nitrogen removal that relies on the use of nitrogen selective membranes. I discuss two types of zeolites that are suitable for the separation task. The company called NGK Insulators in Japan offer membrane modules, shown here, that consists of circular tubes. The inner wall of the tubes are coated with a thin layer of DDR zeolite, and this layer is typically about 20 micrometers thick, and this is the substrate. The DDR zeolite allows selective transport of nitrogen across the membrane, and such units can be used for nitrogen removal from natural gas, perhaps in conjunction with a PSA unit. Let us see how a DDR membrane could be effective for nitrogen removal from natural gas. DDR zeolite consists of cages that have a volume of 278 cubic angstrom, and each cage is separated from an adjacent cage by windows that have apertures 3.65 angstrom in this direction and 4.4 angstrom in this direction. Nitrogen, colored blue, shown here, is a pencil-like molecule whose cross-sectional dimension is 3.3 angstrom, significantly smaller than either of these two dimensions. Methane, on the other hand, has a molecular diameter of 3.7 angstrom and is severely constrained and cannot easily jump from one cage to the adjacent cage. I'm going to show you the animations based on molecular dynamic simulations that illustrate intercage hopping of nitrogen, and you will also note that the green colored methane molecules are unable to cross the windows during the duration of the MD simulation. That is not to say that methane cannot transfer across the windows. It can, because there is some flexibility in the framework that allows diffusion to take place, but that occurs once in a blue moon. Now, I'm going to show you the animations, and I would like you to focus your attention. Well, you can focus your attention everywhere, but especially you can focus your attention on the intercage hopping of nitrogen, and I would like you to observe that this intercage hopping occurs lengthwise. Other animations of MD simulations are available on my presentation on DDR zeolite on my YouTube channel. So let's have a look. Let us now consider the use of Chabazite in a membrane separation process for nitrogen removal. Chabazite also consists of cages separated from adjacent cages by narrow 8-ring windows. The cages are larger than those for DDR, 316 cubic angstrom in volume, and the windows are also slightly larger. The 8-ring window aperture is shown here. It's 3.8 angstrom in this direction and 4.2 angstrom in this direction. So you would expect the diffusivity of nitrogen to be significantly higher than that of methane, because the cross-sectional dimension of nitrogen is smaller than the smaller of these two dimensions, whereas methane is more severely constricted in the window regions. As before, we will see animations that illustrate the window crossing by nitrogen, whereas during the simulation time, methane has not managed to cross any of the windows that is shown here. Other MD animations showing intercage hopping are available in this presentation on Chabazite zeolite on my YouTube channel. I'm going to start the animation, but I would like you to focus your view on this window that gives you an idea about how nitrogen attempts to cross the window. For both Chabazite and DDR zeolite membranes, we performed configurational bias Monte Carlo simulations for absorption of nitrogen methane mixtures, along with MD simulations of self-diffusivities in nitrogen and methane mixtures. By combining the data on mixture absorption and mixture diffusion, we can determine the nitrogen methane permeation selectivity and plot that as a function of the permeability of nitrogen across the membrane. The data for Chabazite for a total pressure of 1 megapascal, the temperature of 300 Kelvin, is shown by this red circle. DDR, because has a significantly higher permeation selectivity, but a lower membrane permeability. The lower membrane permeability is due to the fact that the window dimensions are slightly smaller than those for Chabazite, and therefore the diffusivity of both nitrogen and methane are smaller. But DDR is significantly more selective to nitrogen than Chabazite. It's also interesting to note that both these zeolites, the performance lie in the top right-hand corner of the Robeson upper bound that is described in this paper. I've taken this data in this paper to plot the Robeson upper bound, and most of the data presented in this publication, which is a compilation of published data, lie below the Robeson upper bound. And it is interesting to note that the molecular simulation data for both Chabazite and DDR show that significantly improved performance can be achieved with either of these two zeolites. Now, whether you aim for higher permeation selectivity or higher permeability is a matter of economics that has to be determined from a cost analysis. But we will leave the presentation here with the idea that zeolite membranes using either Chabazite or DDR can offer an alternative to the currently used PSA technology. Another approach would be to combine membrane technologies with the PSA technology to improve the separation performance of the hybrid construct.